the second visitor on our seminars, my colleague, Professor Gong from the University of Jэньmинь University of China. He is distinguished professor of this university. Also, he is Vice Dean of the Institute of Interdisciplinary Science and Director of the Department of Information and Computational Science at the School of Mathematics. Today, he is presenting us his research, deep learning model selection, training, test in computational biology economy. So, Professor Gong, please.
Okay, thank you.
Start.
Thank you very much. Yeah, it's my great glad to be here to talk about my research. Yeah, today I will give you some brief introduction of the deep learning model in computational biology. Yeah, so first is the Google Scholar page. Yeah, Google Scholar page of of myself. So I think the Google Scholar page is very clear here in Illopolis University, but a lot of work in China. So I cannot see this page in China, but I think it's good here. Yeah. So I sorted it according to the citations. I have about 100 papers published in journals and international conferences. Yeah, so about half of the papers is about the mathematical modeling method in computational biology, in protein structure prediction, protein docking. Yeah, the algorithms about fast Fourier transformer and genetic algorithm and graph representation and deep learning, machine learning method. This is about 50 papers. Another half is about using these computational methods in biology. Yeah, we use computational biology methods to help to solve the protein structure, to determine the meaning of the medical images, to find out the gene, the function of the molecules. So this is the Google Scholar page, and this is the ResearchGate page. Yeah, in China we can only see this page. Yeah, I think this the publications and the reads and the citations. Yeah, and this is a Web of Science page. Yeah, because in China we always rank a professor, rank a researcher according to the publications in the Web of Science database. So how many SCI papers have you published? How many citations was about the importance of the journal? So you can see I have published some papers in Nature, in Science, in Plant Cell, and the red, for example, the IEEE, TCBB, BMC System Biology, and the BMC Bioinformatics. So, and so now is the topic the market value of computational biology. Digital economy is very hot now in China, in US. Yeah, especially in Beijing, the government and the corporation put many money into this field. Want us to combine the IT, the information technology, with the BT, the biology technology. So we want to use information technology into biology. Yeah. So the computational biology market report coverage, we can see in the 2022 is about 66 billion US dollars. Yeah, so it's very big. And the computational biology companies, for example, Google DeepMind is very famous all around the world. The AlphaFold, AlphaFold2, AlphaFold3, the AlphaGo, the AlphaZero. AlphaZero is used for the mathematical ring computation. Yeah, the matrix computation, fast matrix computation. And the molecular mind is a Chinese company founded by a professor in protein structure prediction, Xu Jinbo. Yeah, Jinbo Xu. He is originally in the University of Chicago. Yeah, and last year he went back to Beijing to found this new company. Yeah, and the government and the venture capital gave more than $1 million to him to open up the new company to predict the protein structure, to predict the antibody and the antigen interaction. Yes. So yeah, this is deep mind, and this is molecular mind. Yeah. So deep learning in biomedical application, with deep learning at the center of artificial intelligence and machine learning, it should come as no surprise that there are numerous applications of deep learning in biomedical science. But what is less appreciated is that some of the earliest applications of deep learning were precisely in this area, and that the complexity of the problem raised by life sciences have inspired over the years the development of novel deep learning methods. So biology. So originally, is deep learning help biology, and now I think biology is also helping deep learning. Yeah, the circle. Yeah, both help each other. Yeah. So many more and more biomedical applications can use deep learning. So the application areas, for example, original genome, transcriptome, protein, drugs, and many potential uses of deep learning. Yeah. So I have collaborated with experimental biologists and the biology companies to design new drugs for human and for animal. Yeah, and for plant. Yeah, to have the plant to grow bigger and to grow more fruit. Yes. So this is the application. So deep learning method for protein computations. This is my major. My major work is protein computation. So CNN, convolutional neural network. We use it to protein residue contact prediction, protein structure quantity assessment, and deep residue networks, protein contact map prediction, protein distance map prediction. Yes, and GAN, generative adversary network, protein contact map prediction, protein distance map prediction, and the graph neural network. Yeah, and the protein structure prediction, protein molecular docking, and the protein monomer assembly. Many proteins interact together to form a functional supermolecule. Yes, and the transformer. The transformer is the basis of AlphaFold. Yeah, transformer protein dynamic prediction, protein design, and pre-trained models. So now more and more pre-trained models are developed for the different various kinds of applications. So it uses protein representation learning. Yeah, here I will show some of them how to select which method to use for which application. Yeah, to improve the performance. So first is deep learning method for protein structure prediction. Protein structure prediction is from the input sequence, the input protein sequence, and originally used the two-stage method. First is to predict contact matrix. We use, for example, ResLat to predict the contact matrix. There are many methods, for example, Raptor X, triple residue, Kepler lat, etc. And then they use the gradient descendant to optimize the potential energy. Yeah, to optimize the energy formula, energy function. Yeah, to predict the three-dimensional structure, so protein structure. And for example, AlphaFold1, AlphaFold2 are in this kind. And the new development is a one-stage method. For example, they use paired representation and add use paired representation and MSA. What's MSA? Multiple sequence alignment. Multiple sequence alignment. The sequence comparison. Yeah, many different sequences compared to find out the principle inside the protein structure folding. Yeah, MSA representation and add attention mechanism. Yeah, to develop the structure module. So this is a one-stage method. For example, AlphaFold2 Rosetta Fold. Rosetta Fold was developed by Professor David Baker in the Seattle University of Seattle in US. Yeah. And so they use protein non-grid modeling, PM, protein non-grid modeling. And the protein non-grid modeling very famous is the ESM. ESM was developed by the medical school of Harvard University in Boston. Yeah. And OmegaFold is developed by my colleague. Yes, and there are successful applications of deep learning. This is very famous, the AlphaFold1 and AlphaFold2. Yeah, and now we are using this method to predict the protein dynamics. Yeah, and especially the membrane protein dynamics, the membrane complex protein dynamics. So it's very difficult. And I will show you these three topics. First is deep learning approach combining graph representation for multiple protein interaction prediction. And this is the major topic, major research aim in my lab. Yeah. And another is implicit neural network to model the continuous changes for protein dynamics. And the third is pre-trained big model for multiple protein computations. Yeah. Okay. So first is deep learning approach combining graph representation for multiple protein interaction prediction. Yeah. So this is protein interaction prediction. We use these four kinds of methods. First is co-evolutionary analysis, and then we use machine learning and deep learning, and the last is MD simulation. MD is molecular dynamics. And somebody are doing the QM, quantum dynamics, yeah, but quantum molecular dynamics, QM, yeah, quantum molecular dynamics. So it's time consuming, it's computation intense. So we have to improve the velocity of the computation, use bigger super computer clusters. Yeah, one of my PhD students is working in the Microsoft Corporation in Beijing. Yeah, Microsoft Research Center in Beijing. We are collaborating to develop the quantum method to simulate the big protein structure dynamics. Yeah. So, for example, co-evolutionary analysis, very famous is cluster W, BLAST. Yeah, and machine learning, for example, UAFold, SVM, ChemPro, camp. All these methods are using machine learning. Deep learning, rapid X, complex contact, deep contact pre-tool, and this method is using the deep learning tool. And the MD, molecular dynamics. So this is the movie of the dissociation of the two proteins. Yeah. So a pre-training model based on protein structure. Yeah. Pre-training. So we also use self-supervised learning. Yeah. We based on the training network, some representation study the relationship between protein structure and the function. Yeah, so you can see this is the protein structure pre-training method. We can from the protein sequence, amino acid sequence, to get the residue type prediction, distance prediction, angle prediction, and dihedral prediction. Yes, so. And another is mask distance map model. So for example, we can get the random mask and the diagonal mask and off diagonal mask and different of that diagonal mask. Yeah, we use the matrix to represent the contact matrix, contact the distance between the residues inside a protein. Yeah, and protein language model, we use masked language model. Yes, and we use large distance map model. Yeah, this is our pre-training method. We use this mask distance map model. Our paper is this paper is being reviewed in the Nature Machine Intelligence journal. Yeah, we have submitted 2 months ago. Is still in review. So the pre-training of protein structure based on mask distance map model. First, from the mask distance map to get the predicted distance map. Yeah, and then we use the random mask, the block mask, and to get the mask distance map, and added the protein sequence and use the and use the row rotation, low pass, column rotation, low pass, embedding, and transition to, and also we use the triangular rotation. Triangular rotation was first used by AlphaFold, yeah, and we use this to predict the distance map and get the sequence representation. Yes, and after we got the mask distance map, the sequence representation, we can add the global transformation and the local representation. We can predict the 3D structure. Yeah, at last we get the 3D structure. Yes, and the result of protein polymer structure prediction, we structure prediction result on homologous trimer datasets. So three protein interact together to form a trimer. Yes, and this is the index to evaluate the performance. So for the LDDT, the higher the better. So you can see at best we can get about 0.87. So it's very high score. And for the RMSD is the root mean square deviation. Yeah, root mean square deviation is lower is better, smaller is better. So you can see we can get lower as 0.55. In this is the experimental representation. The experimental resolution is about 2 angstrom or 3 angstrom for the X-ray, for the cryo-EM to solve the structure. So if your MSD is lower than 2 or lower than 3, so your prediction is very good. Yes. So at this, we can predict homotrimer, heterotetramer protein structures. Yeah, all of these structures. Yeah. And so this is our method. So why our method protein MDM is better than MF2? MF is a multiple sequence alignment of a monomer, AlphaFold monomer, developed by the Google DeepMind. So they were published in Nature Communications journal. In 2023. So this year we developed the protein MDM to surpass them. So you can see in this hydrotrimer we use protein MDM. We can predict the RMSD lower at 0.6637. Yes, and Pro MDM is better than AlphaFold monomer. So why is that? So we think there are two reasons. The first is the training data. The training data may contain the inter-domain interactions. This will help to correctly predict binary modes. But this information is not used by AlphaFold monomer. And the second is we instead of using the information such as template, we use the distance map to capture the relative positional information more effectively to get the accurate relative orientation between the monomers. Yes. So in this part, so we use the unsupervised learning framework based on mask distance maps. They can be further applied to protein structure prediction of both dimer and polymer complexes. In some protein complex structure prediction tasks, it has demonstrated superior performance. So for future development, further research on protein complexes and ultra-large proteins. But for ultra-large proteins, now it's very difficult for the already known artificial intelligence method. Even the big model, even the pre-trained model, is also very difficult for them. So perhaps we can use quantum computation, for this kind of task. So we are also developing multi-model protein pre-training model. So we use not only the sequence, not only the text, we also use the three-dimensional space information and use the movie, the dynamics movie information, and use the image because from the experiment, they can give us the cryo-EM image, the X-ray image, but all of this information has not been used. So now we are trying to combine all these different kinds of information to develop the multi-model protein pre-training models. So and we also integrate the pre-training model to predict protein function and protein design. Design new protein molecules, for example, to anti-cancer. We are designing the anti-cancer peptide. So this is another part is deep learning method on protein dynamics modeling. This is the movie of the protein dynamics simulation. We use the, for example, in AMBER, in CHARM, in GROMOS. CHARM was developed by Professor Kaplaners in Harvard University, and his student Michael Levitt in Stanford University. They won the Nobel Prize in 2013. Chemistry Nobel Prize for their contribution to the computational modeling of molecules. So CHARM was first developed by Kaplaners in Harvard University, I think about 1970 or 1960, so many years ago. many people are following them. Yeah. So they use empirical force field. For example, the energy total, they use the stretch energy, the bend energy, the torsion energy, the electrostatic energy, the van der Waals, and the hydrogen bond energy and the cross energy. So they combine these energies together. Now, more and more people are using deep learning force field. Yeah, they develop in deep learning force field to do the simulation. For example, the coarse grain LED, CG LED, and the CG stretch LED, flow matching. Many methods are being developed. Yeah, and also use the VAE to predict the residue interactions. Yes. So we can use them to capture the functional information to do the PCA. PCA is a principal component analysis, yeah, a method in linear algebra, yes, and to compute the cross correlation, yes. The interaction analysis in protein multidynamic simulation based on dynamic GNN, graph neural network, yes. So we can publish 3 papers in this topic. Yeah, the first one is 2020. The last one is this year. Yeah, in 2020 we predict the tetramer protein complex from the monomers. Yeah, and we used the originally multidynamics. They use atomic coordinates and velocities, and now we use the input sequence to build the fully graph message passing and to do the FSTM as the long short term memory method. Yeah, this is a machine learning method, and to do the graph message passing with edges and with the MLP decoder. Yeah, this is used in many places. And then we can predict the coordinates at the next time step. So in this way, from the original coordinates, we can predict the next time step coordinates to predict the future dynamics in this way. Yes. And we use the encoder to encode the input sequence, yeah, to get the fully graph message passing, to get the STM parameters. And then we use the decoder to predict the coordinates at the next time step in this way. And yeah, you can see we input only the sequence, and we can predict the coordinates at the future. So, and we use the current time step and the previous time steps to predict the future time step. So the key of protein dynamic modeling is STM. It's a sequence model that encodes add features to their residue interaction at each time step. And we use inferred residue interaction from the encoder to reconstruct graph and predict coordinates at the next time step. Yes? And we can measure the similarity between the prior distribution and the posterior distribution. Yes. So we can show you some results. This is in the protein 1NWD. Yeah, from the step 0 to step 10, step 20, step 30. So we can get the distribution of residue interactions at different time steps. And then we can use the protein domain illustration to show the correctness, to show the correctness of the contact prediction. Yeah. And this is the RMSF. It's different from RMSD. RMSF is the root mean square fluctuation. Root mean square fluctuation of the atom. Yeah. So they can be constructed from the trajectory. The true trajectory, the reconstructed trajectory, and the predicted trajectory. So different trajectories. Yeah. So you can see the truth and the prediction is very similar. RMSF is very similar. Yes. And another protein, 5cc9. So summary of this part, we build a predictive model for protein quaternary structure interface residue pairs, considering the interaction between spatially labeling residues through the structure of the residue graphs. And we used this residue interaction network analysis to analyze the protein dynamic graph neural networks. So to predict the long-range interaction and guide the reconstruction and prediction of dynamic trajectories. Yes. So in future, we also want to do that. So dynamics of ultra-large proteins. So this is also very difficult challenge. Now it's a big challenge in the CASP, critical assessment of structure prediction, international competition. Yeah, this month is still ongoing. Yeah, it will end at the end of this month, from May to August. Yeah. Next is implicit neural network to model continuous changes of protein dynamics. So we are using the deep learning method on 3D representations. 3D representation, so you can see this is a two-dimensional simplified illustration. So we used 3D CNN, and we used the generation network, and this is the meshes method. So worksheets, points, meshes, different representation. Yeah. So based on the discretization of 3D space, and I'm able to accurately represent continuous spatial features. Yes. So the implicit neural representation, the key idea is do not represent 3D shape explicitly. Yeah, and instead consider surface implicitly. Yeah. So as decision boundary of a linear classifier, so we can use the R3. Yeah, the 3D location and the condition, for example, the image, and we can get the occupancy probability 0 or 1. Yeah, for example, this is a 3D representation, a 2D representation, and this is a 3D representation. And the implicit neural representation can use continuous functions to represent a complex geometry without explicit surface representation. Yeah. So we use the signed distance function, yeah, SDF function. For example, let omega is a spatial domain, tau is a temporal domain, and MT is a 3D manifold embedded in omega at time t. So for any point x with the coordinate x, y, z at time t, the function f mt omega to r is defined as. So if the x is outside mt, so it will give the distance, yeah, dx to mt. And is the x belonging to mt, the distance is 0. If is x inside the mt, so it will give the minus distance. Yeah. So where the d we can define it dxy is x minus y. So in this way we can show you the cross-sectional distribution of SDF, side distance function. Yeah, so this show you the zero level set of the SDF can represent the protein surface. Yeah, so we build the DSR model, dynamical surface representation model. Yeah, for the training, this was published last year in the Lure IPS, is an artificial intelligence conference. Yes, and for the training process, we input all the original sequence, manifold points, time, and the space points. We can use our DSR model to build the manifold loss and the normal loss and the gradient loss. So loss is evaluation function. Yeah. So the summing manifold and spatial points at different time points, then adding a temporal dimension. Yes, and the gradient module is a derivative with respect to the x, t. Yes, x is the space, t is the time. Yeah. So lastly is the training process, and then is the inference process. Yeah. For the inference process, yeah, for the grid points at time, so we divide the space into grids based on the desired resolution, and then adding temporal dimension. Yes. And after the DSR model, we predicted the SDF and get the different level sets. Matching cube algorithm is used to generate different level sets. Yes. So totally you can see we can get the SDF of an irregular surface can only be approximated. And the pre-calculated SAF is time and space consuming. So we want to improve it. Yes. So we use the gradient property of SDF. So we prove this. Yeah, the theorem. The theorem, we call it theorem 1. Given a manifold omega, its implicit sign distance function is defined as phi x, with phi x less than 0 in the interior region, omega minus, phi x bigger than 0 in the exterior region, omega plus, and phi x equals to 0 on the boundary. So we can define the phi x function. Yeah, in this way we can prove it. Yes. This is the theorem of the SDF gradient probability. So we use our DSR method to represent the SDF. So you can see we compare the truth with the reconstruction at the different time step, time t0, 5, 10, 15, 20, 25, 30, 35. Yeah, it's similar. And this is the ability of DSR to represent the SDF. So you can see the dynamic representation, the movie, the ground truth compared with the reconstruction. Yes. So this is another result. First is the temporal interpolation. Yeah, this is a numerical computation, and the future dynamics prediction. So we can evaluate the future frames if you can correctly predict the future dynamics. Yes. So we can only use the original structure and very small dynamics trajectory to predict the long future trajectory, dynamics trajectory. So this is important. Yes. So this is a case study. GPCR is a very famous, important protein class. For example, for humankind, I think more than 80% drugs are targeted at GPCR proteins. Yeah. So this we calculated the reconstruction and compared the reconstruction with the ground truth. Yes, and we also did the calculation on DIMS. We can see the ground truth, the prediction, and the comparison. So it's very similar. Yes. So in this part, we summarize. We propose a method to learning the implicit neural representation of protein surface dynamics that allows for continuous time and space representation of protein surfaces, and the dynamic exploration of unresolved protein structures. Yeah. So for future development, yeah, we use general models such as diffusion models. Yeah, to generate more diverse dynamics from limited space on latent vectors. Yes, and enable the model to portray some properties of proteins such as electrophoric mobility, hydrophilicity, etc. So that the model can be better applied to the prediction of protein functions. Yes. So the last part, the last part is a pre-trained big model for multiple protein computations. So deep learning method on protein representation learning. So first is the sequence representation learning, the NLP, natural language processing based method. Yes, for example, TAPE, ESM1B, ProTrans, ProGen, XTrimer, PGM. So they do the pre-training, predict masked tokens. Yes, so ESM and ProTrans and ProGen and XTrimer, PGM. And another kind is new kind is the structured representation learning. So for example, 3D CNNs, GNs, contrastive learning pre-trained method. We can do 3D CNN, GNs, contrastive learning, and pre-trained method. Yes. So existing method and limitations on protein structure representation. So in this paper, in our paper, we want to surpass them. We want to solve these difficulties. So, for example, the methods and limitations for the contact and distance method, they lose critical spatial information. For the surface-based method, they fail to model internal structures. For 3D voxelization, the trade-off between the accuracy and the computational cost is very tricky. Yes, for the graph-based method, suboptimal performance in long-range interactions. So they cannot succeed in long-range interaction. And for the sequence-based pre-training, so the same sequence may need different structures. So this problem is difficult for them. And for other existing pre-training model, only tailored to specific tasks. Different pre-trained model for different tasks. But not universal. So an effective self-supervised task can capture the complex long-range interactions and multi-scale information inherent in three-dimensional protein structures, facilitating a comprehensive understanding of protein structure. Yes. So we developed a new versatile structure, understandable protein pre-training model. So I can publish and put this paper on archive. So you can see the PDF on archive and all the programs, all the codes, and all the data. Can be downloaded freely. We call it SABLE. From the pre-training, we use PDB protein data bank, and we can calculate the distance encoding and the spatial position encoding, and we can do the mask token and coordinate noise and do the encoding to get the relative position encoding, and added together we can get the atom distance restoration and mask token prediction. Yes. And then we use transformer to do the single representation, pair representation, and so this is the fine-tuning. We use the labeled protein and to do the trainable pre-trained SABLE. And we use the trainable task layer, for example, MLP, and to do the predictions. And then we use them in different downstream tasks. So we call it versatile. Is this meaning? Not specific for specific tasks, but it can be used for many tasks. Only one pre-trained model. For example, this is the regression. We divided into 3 kinds. Yeah, first is the regression, model quantity assessment, binary affinity prediction. Yeah, and the second kind is classification. For example, fold and enzyme catalyzed reaction prediction, and goal-term and enzyme commission prediction classification. And the third is generation, protein design. Yeah, design a new molecule not in nature. And antibody design. Yeah, antibody design is very hot in big pharmaceutical companies. Yes, in digital economy. Yes. So this is our level structure encoding mechanism. Yeah, we use SPE, spatial position encoding. Yeah, we use the local coordinate system. For example, this is a local coordinate system of the residue, and we did the binning in 3D. Yes, and we do the distance encoding, and and the projection of the fine-grained distance information show you the projection. And we did the self-supervised task to first enhance the robustness of the reconstruction process. We add a set of laws to the coordinates. Yeah, for example, this the law is if the ik, and if the ik we define it is alpha multiplied with eta ik. So this here, the parameter alpha is sampled with different probabilities. Yeah, from 0, 0.1, and 1. Yeah, and the disturbed atomic coordinates to alter the relative position of residues. Yeah, to enhance the robustness with the noise. Yes, and the perturbation of coordinates introduces noise into the distance information. Yes, in this way we can recover the distance information between the atoms through pairwise representation. Yes. So we show you some result. This is a regression result, comparison evaluation of SABLE and baseline methods on model quantity assessment and binding affinity prediction tasks. Yes. And SABLE has achieved the state-of-the-art performance on various evaluation metrics in CASP 14 and CASP 15 tests. And also SABLE can predict the impact of any type of mutation without any mutation. So we can mutate the residue, 1 residue, 2 residue, 3 residue, different kind of combinations of residues. We can evaluate compute the affinity, binding affinity change upon the mutation. Yes. So this is a result of classification task. Overall comparison between the SABLE and other methods for protein function. So protein function, many methods are in this field. Yeah. So we predict the fold, the superfamily, the family, the EC. These 4 are used for the function classification. Yes. And the last is generation task. Yes, we explore SABLE's performance in generation task and the impact of data scale on pre-training performance. Yes, so antibody sequence structure co-design the antibody sequence structure and antibody-specific antigen-specific antibody design. Yeah, so that's all. Last is acknowledgement. Yeah, this is my team. So, but I cannot show it. Yeah, and at the upper left is the newest picture photo of this year. Yeah, when our new center in Shenzhen. Yeah, Shenzhen is a city, a new city in the South China. So we built a new center for applied mathematics. I'm the director of the new center in Shenzhen. So you're welcome to Shenzhen. Yeah, about 3,000 kilometers from Beijing. So, But here from Beijing is about 8,000 kilometers from here to Beijing. 8,000 kilometers. Yeah, it's far. Yeah, and on the right, upper right, is last year my student graduate, my PhD student graduate. Yeah, and the lower left is the year before last. Yeah, a student graduate, and the lower right. Yeah, last year we went to the mountain Tai. Do you know the mountain? The mountain in Shandong province, very famous. In China, there are 5 famous mountains. Yeah, the poem said if you climb the mountain Tai, so all other mountains are small. Yeah, yeah. Okay, that's all. Thank you. Thank you very much. Yeah. Oh, sorry. Why? Thank you. Yeah.
Thank you, Professor Gong. Few questions. First, for me, it's interesting when you apply deep learning approaches for molecular dynamical simulations. For me, it's interesting how the main point here is the computational acceleration, right? Because, for example, if we're using classical approaches which are realized in such tools like GROMACS or Chamber or some kind of coarse grain models, yes, we are typically thinking about the time of simulation. For example, in the 2010s, when we use GROMACS for molecular dynamical simulation for 2 proteins docking, it takes maybe at least 2 weeks, sometimes 1 month of GPU simulations for one trajectory. Yeah. So it's very huge time and a lot of resources. So my question is, and of course we are using cross validation between some different approaches. For example, we're taking some parameters like force field parameters from GROMACS to coarse grains models to accelerate our simulations. That's questions. How fast first deep learning approaches, and do you have some interchange of parameters between classical approaches and with deep learning methods?
Yeah, thank you. Yeah, this is a very important question. Yes, for traditional molecular dynamics, so there are 2 difficult questions. First is time-consuming. Yeah, very long time computation. And even you use all the computers, we cannot get the functional state. Yeah, and the second, another very difficult problem is the energy function. Yeah, because we cannot accurately compute the Gibbs free energy. Yeah, free energy, we can only approximate it. So, yeah, so I think in my lab we have 3 methods to improve, to accelerate the simulation. Yeah, the first way is we only do the coarse grain simulation. Yeah. For example, I have published 2 papers in Nature to use the coarse grain method to simulate the membrane protein complex. Yeah, not only protein but also with the membrane. Yeah, the lipid membrane. So, but at the first step, I transform the coordinates, atomic coordinates into the coarse grain. Coarse grain, every residue I only use 1 point, or every domain. For example, for the multimer protein complex, for every domain I only use 1 point to represent the whole domain. So in this way, we accelerate the velocity. This is the first method. And the second method, we use the we use the deep learning to predict the future dynamics. We do not really simulate the dynamics. We only simulate a very short period at the beginning, and then we use GROMACS, and AMBER to simulate the protein atomically, full atom simulation, but only a very short period. And then we use this short period trajectory to predict the future trajectory using deep learning. Yeah, deep learning. So we use this new surface representation, not atomic representation. Yeah. So we change the problem, more complex problem to simpler. Yes, this is the second method. And the third method in my lab is to combine, for some chemical reaction, it's very important to take into account the reaction. So, for example, the electron transfer. So this is very difficult for simulation. So we combine the quantum mechanics computation with molecular mechanics computation and with deep learning. So we combine these three kinds of computation. For example, in my lab, we are developing a new method to divide a big protein into smaller parts. Yeah, into many parts, and we simulate the small parts. Use many computers at the same time, using quantum dynamics, using quantum computation (QM), and then we combine all these quantum computations together. Yeah, to get the whole picture. Yeah. So in these three ways. Yeah. Thank you. So thank you very much.
Any more questions? Okay, but it's interesting.
Yeah.
What was the acceleration when you use, for example, GROMACS, you produce short simulation, and when reproduce this simulation by using deep learning models? Yeah. How fast was the acceleration when we use deep learning in compare for GROMACS or AMBER?
I think more than 1,000.
More than 1,000.
Yeah, more than 1,000. Yeah. For example, if you only use GROMACS, you cannot get the functional state of at the time scale of
nanoseconds, probably. Yes.
Microsecond.
GROMACS, yes, microsecond. Yes.
Yeah. You cannot get that. Yeah.
But really, we need seconds at least.
Yeah. Yes. But in deep learning, we can get that.
Yeah. It's nice.
Yeah.
A very good result. Okay. Any questions from online? Oh no. Okay. Thank you, Professor Gong, for your beautiful presentations and very interesting research. Hope you see next time again in our university. You are welcome. And we will be glad to collaborate with you and produce some interesting research. Thank you.
Yeah, thank you. Thank you very much. Yeah. Okay, that's all.